So this is the transfer function model of the DC motor. We are going to convert into state space, and as you can see, it is a model that represents how the motor speed is related to the applied input voltage. So the first thing we are going to do is to cross multiply, and as you can see, it is in S domain, so we have to convert it into time domain. So we do the conversion using this table, and you can see the left hand side is the power of S and the right hand side is its time domain equivalent. So S x is just S dot, and S squared S is S dot dot up to the power of n. So applying this transform, equation 1 will turn into equation 2. So now this is the most important part of this conversion. So a transfer function model may have different state space model equivalent. The conversion depends on how you define your states. So different definition of states will give you different equivalent for the state space model. So in this case, our definition is I define my S1, the first state, to be omega, which is the output as you can see from the transfer function model, and my S2 to be omega dot, which is the motor acceleration. So from A, my S1 dot, if I take the derivative of S1 dot, you can see it is just S2, and my S2 dot is just omega dot dot. So applying A and B into 2, I will get this equation. So making S2 dot the subject of the formula, I will get C. So from A and C, my state space equations are just this. So I have S1 dot and my S2 dot, which is the state equation, and Y is equal to S1 is just the output equation. So arranging in the general matrix form for state space model, that is S dot is AS plus BU and Y is equal to CS plus DU, I will have my state equation matrix, which is this, and my output equation matrix, which is this. Therefore, from these two equations, my A, B, C, D matrices are this. So this is just one state space model equivalent of the transfer function model. Let us look at another definition of states. So now defining my S1 to be omega dot and my S2 to be the motor speed, which is the output, I will have S1 dot to be equal to omega dot dot and my S2 dot to be equal to S1. So substituting D and E into the general equation, I will have this equation, and making S1 dot the subject formula, I will get F. So from E and F, my state space equations are these equations, and arranging in matrix form, I will have different state space model where my A, B, C, D matrices are this. So as you can see, I have two different state space model representing the same transfer function model. So let us see how this can be easily done in MATLAB. So here we are in MATLAB. This is the transfer function model I want to convert to state space model, and I need my A, B, C, D matrices. So I declare them as my output A, B, C, D, and then I use the function transfer function to state space, and it carries two arguments. The first argument is the coefficient of the numerator, which is 1, and the second argument is the coefficient of the denominator. So I have the coefficient of S squared is 1, the coefficient of S is 100.1, and that of the constant is 11. And pressing enter, I will have my A matrix, B matrix, C matrix, and D matrix. So if you want to learn how to convert state space model back to transfer function model, watch the video on the screen. Please like and subscribe to this channel. Thank you for watching.